Here's oxygen. I'm going to write OX so you don't think this is a little circle, because previously we've done the S and P orbitals like this, right? The S and then the 3P orbitals. We're going to change that a little bit because the book uses a slightly different motif, and since you need to be studying from the book, I'm going to use their motif now. Here's an S, and here's your 3P orbitals, right? This would be your PX, PY, PZ, and here's your S. Yes? Okay. Now, again, oxygen is S2P4, and so that's 1, 2 in the S, and then 1, 2, 3, 4. Otherwise known as this in the Lewis dot diagram. Here's your S electrons, here's this, and I'll do it like this, for the heck of it. Alright, so what happens when we have a covalent bond, the way that you need to think about this is, it's much more specific than this. This is just the general idea. Here's hydrogen. Here's hydrogen, and it looks like this, right? Because, wait. Hydrogen is just 1s1, and so here it is, and here's hydrogen's Lewis dot diagram. Is that hydrogen is going to pull up here, and it's going to share. And here's the other hydrogen. It's going to pull up here, and it's going to share.
Wait, there's two hydrogens?
Well, right. Remember, that's what we had before. Remember, we had oxygen with the two hydrogens attached to it. And so, what we're actually seeing, folks, here, I know that we've been getting off task a little bit, and I know I just spoke in Spanish about maybe taking the test a different day, but and got everybody.
Were you serious about that?
Yeah. Sí. Por supuesto. But
What is that?
let's talk about that later, okay? I don't want any record of me being reasonable. Okay. What's going on here, folks? You have to understand. This is hydrogen number 1. This is hydrogen number 2. So, like, let's call this one number 1. This one number 2. So, what's really happening is this is the shared electron. So, what's really happening is that they're sharing between the empty orbital on the oxygen and the hydrogen, both of which need 1 to be full, right? Notice how the full ones don't interact at all. The ones that already have 2, they don't interact. It's the ones that have only 1 that interact. And here's hydrogen number 2, which bonds by sharing between the 2 orbitals. So it really shows how what they're actually doing isn't just, yes, they're filling the octet, but they're filling it by sharing between half-full orbitals. And if you want to look at it like a Lewis dot diagram, here, we'll make hydrogen blue so that there's a little bit of contrast. It looks kind of like this. So once again, like this is this full orbital from oxygen, which isn't participating, and then this is the other full orbital from oxygen, which isn't participating. This is the half-full orbital from oxygen sharing with the half-full oxygen from hydrogen, and this is the other one. And so what this Lewis dot diagram of a compound is now showing is the sharing that's going on. See?
Oh, so sharing so it makes full equilibrium.
That's right, full octet. And then, so what you want to do to make sure that it's done correctly is you want to count the electrons. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. Hydrogen has 2, which is all hydrogen needs. Oxygen has 8. Everybody's happy. Half-full orbitals are now effectively full. So think about that for a second while I prepare this side of the board for the next example. Does anybody have any questions about that? Oh, by the way, wait. back to what I promised, which was that we would just explain what this means. So bonding, I think we understand. Bonding is bonding. But covalent. So what's really going on with covalent bonding? Co, together, and valent, meaning the outer electrons. I don't know the Greek root or whatever. I'm just saying covalent. They share their valence electrons, so that everybody can be happy.
Valence?
Yeah.
Valence electrons are your outer electrons.
Sorry if I'm not smart.
Nitrogen is S2P3, right? And if you look at nitrogen over there, it's in group 5. It's, let's do this too. If we were to look at nitrogen, it has a full s orbital and then 3 half-full p orbitals.
Found it yet?
Are you talking to me?
No, I was telling
Okay.
you it was number 7.
And, all right, I'm going to do, here's the, here's the S and the P. Here's the full s orbital. Here's the 3 half-full p orbitals. Can you already hopefully start to see where this is going? Why we have 3 hydrogens in NH3?
Yep.
It's because there's 3 half-full orbitals, and so when hydrogen, which is still that, color coding, still that, hydrogen comes along, it's going to, here's hydrogen number 1, hydrogen number 2, hydrogen number 3. Each of these brings an electron to the party, and so they're all going to be able to share. So there's sharing between these two. So if we draw, there's a lot of ways to draw this. Here's one. That's another way to do this. And so like this is a stick, like a ball and stick figure, I guess it's called. And what this really represents is the 2 shared electrons. And so like this would be this bond, and this line would represent this bond, this line would represent this bond. And so that's your three hydrogens, each of which is sharing 1 electron. And I'm gonna actually I'll also show you the Lewis dot diagram, which looks like this. And I want to show you one more thing, just to make sure people are down with what I'm talking about. Are you down? Word. Okay. Also on tape saying that. Let's let me try to draw one more thing, and then I'll back up for a second and let you collect your thoughts. So here's the 2s and 2p orbitals of nitrogen, right? Just to review, we have our s electrons. I'll do them in red, which we know aren't going to really participate. I just kind of want to put them so they'll be out of the way. Here's the here's a p orbital. Here's the p orbital in the y-axis. Here's the p orbital in the x-axis. And here's the p orbital in the z-axis. This is the last sort of new wrinkle on this. And so if we draw the nitrogen as it is beforehand, before it bonds...
It's going to have 1 in each of those orbitals.
Yes, exactly. It's going to have 1 in each. So, like, here's one on the x-axis. We could say that's this one. Here's one on the y-axis. And here's one... Whoops! See, that was a mistake. Here's one on the z-axis. Right? So 1, 2, 3, 4, 5. But specifically, 1 in each orbital, and then you have the 2 that aren't going to interact at all because that's the full s orbital. So what the hydrogens actually do is they come here, here, and here, each bringing their electrons. And so that's what's actually happening. It's a little more complicated than the Mickey Mouse thing I drew before. But
Hey.
Nice. Hey, we're taping here.
Sorry, Mr. Auerbach.
Thanks, Alyssa.
I didn't mean to.
Like how you know who it was.
All right. So there's like let's say that's this one. So that's the shared. So there's really only 2 shared electrons per orbital. And here's this one. Oops, going around. I have a harder time drawing this. And here's this one. But the point is that everybody's sharing electrons, and it's really a wonderful, happy little world we have here, even though it stinks because it's ammonia. All right. Are there any questions about that? Let's put I'll put our Lewis dot diagram back. Okay. All right. So, yes.
Why do they use the S orbital and P orbital and B and F and why do they pick those letters?
Physicists, and physicists are kind of like tech people. It's like you ask them a question, and any specialist like gives things in a way that makes sense to them, and not a way that's going to make sense to the common person. So if they thought this through and say, okay, for the next 120 years, regular people are going to have to learn this. Let's come up with a way that regular people could understand. No. They're like, we're going to call this one the S orbital. There's reasons behind all of them, but they just, it's geek reasons, geek reasoning, which is fine. It makes sense once you understand it, but, unfortunately, I'm your interface between this world and this world, and so I'm sorry is all I can say.